Okay, let's go for the next topic. The next topic is going to be refraction of light and lenses. When we're dealing with light and light goes from one medium to another medium, it happens that light bend, right? Refract. For example, imagine that we have air, right, and we have glass. When we have an incident ray, right, on this interface, light is refracted, is bent. If this index of refraction is larger than this one, right, the second one, light refracts toward the normal. This is called the normal. Every time we have a surface, right, it's very common to use a perpendicular line, right, and this line is called normal, right, the normal. When we have forces, we call this the normal force and so on. That's the case right here. We have a surface, so we have an incident ray. So the incident ray has an angle, right, respect to the normal. We call this the incident angle. And later what happens? It refracts, changes, right, in direction. And we call that angle the refracted angle, correct? And this medium is represented, right, by a quantity that is called the index of refraction. Index, right, of refraction. This index of refraction is defined as, right, the speed of light in vacuum divided by the speed of light in the medium, transparent medium. Of course, right, this index of refraction usually is greater than 1 because the speed of light in the medium is less than the speed of light in vacuum. Okay, great. Now, what happens later? We have this interface, correct? This is air, right? And this is glass, right? Of course, the index of refraction for air is less than the index of refraction for glass. When that happens right here in this interface, light is refracted toward the normal. But now let's go for the case when light is leaving the glass, right? So it goes from index of refraction of the glass to index of refraction of the air, which is the opposite. Means that light refracts away from the normal, correct? Perfect. Now let's try to find an equation that helps us to study the relationship between these two angles and between, right, these two index of refraction. The index of refraction is kind of the optical density, right? Okay, perfect. Let's do it. Imagine that we have this interface, right, represented by this line, correct? And we have the rays coming right in this direction. Parallel rays means that maybe the source is far away, or maybe it's a laser. Why not? Okay, perfect. Let's see what happens then. So we have a wave, right? Imagine these are the wave fronts right here. These are the wave fronts in this way, right? These are the wave fronts, right? And from here to here we have this one lambda, right? This lambda. Of course, it's another lambda. But as you can see, lambdas are different, right? Let's call this distance, right? This distance, the wavelength. Let's call it d1. d1 equals to, if we relate distance with speed, remember, how do we find speed? The speed is defined as distance divided by the time, correct? Let's solve for the distance, and what do we have? Distance is v1 divided by time, time 1, okay, time 1, okay, perfect. What happens right here? For this case, the same thing, right? This distance of the wavelength, right, equals to what? Equals to d2, right, equals to v2 times t2. Perfect. As you can see, the distances are a little bit different. How we can find the distances then? Well, remember, we create a line perpendicular to these two lines, right? It's perpendicular. Same thing happens right here, right? But because light bends, this section becomes smaller, means that the wavelength is less. But what happens then to the frequency? The frequency is the same. The frequency is the same in these two mediums, but the wavelength is different. Okay, great. Now let's see what happens. Well, look, right here we have this angle. Remember, let's use as similar triangles. Look, if we have this, let's take this picture. If we have this angle right here, right, theta, right, then we have another angle that's formed by these two lines. This line is perpendicular to this, right? and this line is perpendicular to the other one is found by geometry. These two angles are the same. Okay, this is by geometry. Perfect. Let's use this concept right here. Look, we have this line is perpendicular to this line, and this line is perpendicular to this. Means that these two angles are the same. Correct? Now, let's go to this other triangle. Look, this line is perpendicular to this line, right? And this normal is perpendicular to this horizontal surface. Correct? Means that these two angles are the same, too. Perfect. Now let's find a relationship, right, for these two angles. Perfect. Now look, we have these two angles like this. We have this one in this way, correct? That one in that way, in this way, correct? We have another one like this, and like this. Okay, this is gonna be the incident angle, right? And this is the refracted angle. Right, this is right angle, right, and right angle. Let's share the same side. This one, let's call this side B, for example. Okay, and now let's use sine, right? Sine, right? Because this is this line, this given. This is D1, right? And this is D2. Perfect. Now, what should be then the answer? Okay, sine theta initial incident equals to what according to this picture is gonna be D1 over B, correct? What about for the other angle, right? Sine theta refracted, right, equals to D2 divided by B. Okay, they have something in common, right? What is that quantity B? What happens when we divide these two? Let's divide these two. When we divide these two, what do we have? We have, look, we have that sine, okay, sine theta incident equals to Bi over D over B, right? Over B right here. Perfect. Over B in this way, right? That's gonna be D1 over B, right? And we have sine theta refracted equals to what? The 2 right over B. So B's cancel, and then we can rearrange it if you want to. We have sine theta incident over sine theta refracted is equals to D1 over D2. Correct? Perfect. Now let's use these conditions right here. Okay. Let's do it. Let's do it. And then sine theta incident, sine theta refracted is equals to D1 by D1 is equals to B1 T1, right? Divided by D2 T2. By the time is the same, right? T1 is equals to T2. Correct? Something wrong? Okay, gonna be V2 right here, V2. When that happens, right, what do we have? We have that, let's arrange it this way. We have that V2, correct, sine theta incident is equals to B1 sine theta refracted. Correct? Perfect. Now, let's use the inverse refraction definition, right? N is equals to the speed of light in vacuum, right? Divided by the speed of light in the medium. Okay, when we solve for V, right? V is equals to C over N, right? We will call this V1, it's gonna be N1. C is constant, right? In this medium and in this medium. Well, this is actually in vacuum, right? It's in vacuum for this case. Okay, perfect. Now, let's substitute this value, right? Right here, correct? And then what do we have? We have that V2, again we call this V2, it's gonna be N2, right? And so on. Okay, great. So it's gonna be C over what? V2 over N2, right? Sine theta incident, right? Equals to V what? Equals to C over N1 sine theta R. Okay, look, let's match the actually C is cancel, right? Now let's match the subindices right here, right? I call this theta incident, or I can call it also theta 1, and right here I can call this theta 2, right? To match this subindices right here, right? Okay, perfect. When that happens, right, we rearrange this, and what do we have? We have this equation. We get this very famous equation in refraction. It says then that n1, right, sine theta 1, correct, is equals to n2 sine theta 2. This is called the Snell's law. Snell's law. Okay, again, this gives us the relationship between the angle of incidence, the angle of refraction, and the index of refraction for the two mediums. Okay, or the two media. Okay, perfect. Great. Now let's go to the next topic. The next topic is gonna be the apparent depth. Okay, let's see how we can find it. Okay, we have time. Yeah, we have time. Okay, let's go to the apparent depth. Okay, hopefully we have enough time to finish this section. Okay, let's do it. Let's do it. Imagine that we have a medium right here, water, right? And when we have a person right here, right, looking at one object right here, right? So we have light coming in this direction, imagine, and refract, right? Light is coming from the source, which is the object right here, correct? Perfect. Now this is the normal. Of course, this is the incident angle and this is the refracted angle. Okay, great. Now, this observer sees this object right in this direction, right? The object is actually right here, correct? This is the apparent depth, okay? Apparent, right, depth, apparent depth. Okay, let's do it. So let's call this height, let's say, or depth, right, h, and this is right h prime, or d, we can call it d, the distance. Okay, distance, perfect, distance. This is the original distance, right, and this is the apparent depth or distance. Perfect. Now look, what do we have? Let me try to enlarge this situation right here. Look, we have that this is let's project this line. Look, this line, which is this one right here, right? This is the distance from here to here, right? D prime, right? And this is the normal, and we call this, remember, this an angle. So these two angles are the same, right? These two angles are the same. So this angle, this one and this angles are the same. Perfect. Now let's go to this line right here. This one, the refracted one, correct? This is now the refracted one, like this, right? This is the refracted one, like this, right? Like that. Now look, this angle is the same as this angle too, right? These two angles are the same, correct? But they share the same side. This one, let's call this side again what? A. Okay, A. Perfect. And now let's go to find tangent, right? Look, we have two triangles. We have this triangle right here, right? This one, this is D prime, and this is theta incident. This is A. From this triangle, we have tangent theta incident, right? Equals to what? A over D prime. Now we have another triangle, right? This triangle, the largest one, let me do it right here, right? This one, these two angles are the same, right? And the same thing right here, tangent, right? Theta refracted. Now this is theta refracted right here. Perfect. Is equals to A over D. Correct? Now, for small angles, right? For small angles, sine theta is about tangent theta. Correct? Perfect. Now we can use the Snell's law right here for this equation because we're dealing with refraction. correct? Okay, let's do it. Let's do it. Let's do it. So what do we have then? We have that instead of sine, we use tangent, right? We have n1 tangent theta 1 is equals to n2, right? Tangent theta 2, correct? Perfect. Remember, n1 is gonna be related to the mirror, right? To the incident ray. Perfect. Now, but what is sine theta 1? Is a over d prime. So we have n1, right? A over d prime, correct? Equals to what? Equals to n2, right? A over d, correct? Let's rearrange it. Remember, we're looking for d's, right? D prime, which is the apparent depth. Okay, perfect. Now let's solve for d prime. So d prime is equals to what? Is equals to n1. That's correct. N1 actually is this. Look, be careful with this. Okay, this is the incident. So this is the section for the incident. It's gonna be D, right? And this is the refracted, right? The refracted, right? This is the incident, and this is the refracted. This is the angle are refracted. This is D prime, correct? Got it? Perfect. Now what do we have? We have to change it right here. It's gonna be D, and this figure is gonna be D prime right here. Okay, perfect. Now let's go to solve for D prime one more time. So D prime, right, is equals to n2 over n1, correct, times, right, D. But remember, n1 is the initial refraction of the glass or water in this case, right? And n2, right, is the initial refraction of air, right? N2. So what should be the apparent? This is larger than this one, so the apparent depth is less than the actual depth, right? Got it? And this is the formula again for the apparent depth. Okay, great. Now let's go to the next topic, which is the total internal reflection. Let's do it. Total internal reflection. Too many topics, right? Too many topics. Let's do it. Total, right, internal reflection. Perfect. Total internal reflection. Great. That happens again when light goes from a index refraction, right, larger, the incident index refraction is larger than the refracted index refraction. For example, if we have water and air, right? When we have water or glass, right? Let's say water and we have air right here. So what is happening? Well, if we have a ray coming in this direction, right? We know that when we have this condition, this is the incident ray. So this is the normal. The refracted ray is refracted away from the normal, right? This is the original path, right? The original path. So it's gonna be not toward but away from the normal, like that. Correct? Let's take another angle. The same thing, right? This is the normal. This is the original path, like that. So the ray is refracted away from the normal, right? Away, like that. Actually, in this interface also we have reflection, right? We have some amount is reflected, some amount, small amount is also reflected right there. Perfect. Now what happens? We are not paying attention on this rays, right? We're paying attention on refraction. Okay, perfect. Later is found, right, that at this angle, some angle, right, the ray is refracted parallel, right, to the surface, correct? And after that, if we increase the angle, right, one more time, now all the ray is reflected toward the same medium, toward the incident medium. Okay, and we call this total internal reflection, correct? Why is total? Because the total light is reflected. As I mentioned before, right, we have some fraction right here, some fraction right here. But right here, the total light is being reflected toward the same medium. And we call this the total internal reflection. Okay, this angle, the maximum angle that produces refraction, right, is gonna be this case, right, at the maximum angle. This angle is called the critical angle, this one. This is called the critical angle, which is the same, right, as this, right, incident angle right here. Right, now how we can find this critical angle? Well, we use Snell's law. Okay, let's do it. So what happens right here? Look, the refracted angle theta 2 is equals to 90 degrees, and the incident angle, right, is equals just to the critical angle. Okay, let's then apply Snell's law. What do we have? We have the incident refraction, right, times sine theta 1 of incident angle, right, is equals to the refracted refraction, right, times sine theta 2 of the refracted angle. Perfect. But what is the refracted angle? 90 degrees. Sine 90 degrees is equals to 1. Correct? And in this case, where this is the angle is 90 degrees, this becomes the critical angle. Correct? Perfect. Now, how do we find then the critical angle? The critical angle is equals to the inverse sine of, right, n2 over n1. Right? And this is the way how we